Hello, Professor.
Hello, hi everybody.
Hi.
How are you doing?
Afternoon.
Wait, do we have a quiz on Friday?
No, we don't. Where did you see a quiz?
Oh, sorry, I just thought I heard something about quiz. My bad.
No, we said homework was due on Friday.
Oh, okay. All right, thanks, man.
Okay, so what we are going to do today, we will finish our discussion for circular motion, and we're going to talk about Newton's first law. We'll move on to talking about forces and motion, Newton's laws. So hopefully today we'll finish Newton's first law. Okay, so continue with our discussion for circular motion. Just 1 second, let me share my screen. So we talked about, even though that the velocity, the magnitude of the velocity for circular motion is constant, because the direction of the velocity is still changing. That means that there is a required acceleration. This acceleration can be calculated by doing dv over dt, right? Velocity over time. And because dv, we have shown to be v d theta, so it's going to be v, a constant speed. V is your speed, d theta over dt. Now, this is an angular velocity, omega. This is called angular velocity. We're going to talk more about it later, and we do angular kinematics in the later chapters. But here, I just wanted to mention the name. So it's the rate of change at which the angle changes. So you can say angular velocity could be pi radius per second, meaning that in 1 second, your rotation is 180 degrees, how fast something is rotating, right? Or it could be 360 degrees per second, meaning that in 1 second, this thing rotates all the way around. So that is described by omega, the angular velocity. So d theta over dt is omega, which means your acceleration is velocity times omega. But at the same time, velocity is omega times r. So how did that, okay, so where do we get this relationship? Now, if you think about if something rotates all the way around, right? So it had gone through 2 pi r circumference in certain amount of time. So that gives you the speed, right? The linear speed. In terms of the angular speed, that's 2 pi. It goes all the way around 360 degrees in the same amount of time. So that's omega. So that's why your v is omega times r. That's how these two are related to each other. So because v is equal to omega r, we can represent our acceleration using just v or just omega. If you're using just v, acceleration is v squared over r. If you use just omega, is omega squared times r, okay? Because v and omega are related. So this is what we call centripetal acceleration, because the acceleration is always points toward the center. If it's always pointing toward the center, this acceleration will only change the direction of your velocity, but not the magnitude of your velocity. So this is what we call centripetal acceleration. So you can use a subscript A, subscript C to represent it, which is v squared over r, okay? So for example, let's look at this question. If we are looking at a car traveling at constant speed, right over the top of a hill. Now at the top of the hill, the acceleration is pointing in which direction? On this one, I will talk through it. I won't let you vote. Later on, we'll have a question for you to vote. Now you can see this hill looks like a just a section of the centripetal motion, the circumference. So at the top of the hill, and the car is moving at a constant speed, right? At the top of the hill, the car is moving with this speed tangential to this direction. So your centripetal acceleration will be pointing directly down. That is perpendicular to your velocity. And it's changing the direction of your velocity. So it's pointing downward, okay? Now, this is just a summary of we talked about the direction and magnitude of your acceleration. Now, this acceleration, as we said, is perpendicular to your velocity and only changing the direction of your velocity. But if you do need to change the magnitude of your velocity, then your acceleration has to be either in the same direction, you need another acceleration. If you have another acceleration that's in the same direction of your velocity, then it's going to make your velocity increase. It will make you speed up, right? If it's in the opposite direction, then the velocity will decrease and you will slow down. So in real life, a lot of times you're changing both the magnitude and the direction of your velocity. So you can imagine as you go around the curve, not only you are changing the direction as in you're going in the curve, but you're also maybe speeding up or slowing down. Now, in that case, we choose to look at these two accelerations as in the one that changing only the direction, that's called the centripetal, or the one that's making you actually speed up or slowing down. So you need both of them to make that change. So this is a question for that particular case. In this case, we have an object that's moving along a circular path, and I'm showing velocity at two different times. One is v1, you can see is in this direction, v2 is in this direction, but v1 is also bigger than v2. So not only this object is curving around, is also slowing down. So in this case, which of these arrows, A, B, C, D, E, which of these best represent your acceleration at point X? So X, imagine X is a point in between V1 and V2, okay? And you can think of V1 and V2 are still pretty close to each other. So within this short amount of time, what is the acceleration that is needed to make the object not only change directions, but also slowing down? So I'll let you take a screenshot of this, and then you can discuss in the breakout rooms for a couple minutes, okay? Okay, now again, if you're somehow you're in the room that people are not active, you can come back to me and let me assign you to another room. Okay, another 15 seconds for us to finish voting. Okay, I'm gonna go ahead and close this and let's take a look. Here's our results. Majority voted for D. The second popular answer is E, and you can see that they're roughly in the same direction, right? Sort of to the left, but D is just a little bit more downward. So let's take a look. Would anybody like to share with us that what method do you use to figure out the direction for your acceleration? Given the two velocity vectors, how do we figure out?
I knew there was some centripetal acceleration towards the inside of the circle, so that meant it couldn't be B or C.
Okay.
And then it's also decelerating, so the forward direction is getting smaller, so it has to be acceleration towards the negative Y. So that's why I came up with D.
Okay, Clement, thank you so much. That's an excellent idea. So if it's only doing circular motion with a constant velocity, then we need a centripetal acceleration pointing to the center perpendicular to your velocity, right? However, it is also slowing down, meaning that you need another acceleration, and we call this the tangential acceleration. That is in or against the direction of your velocity. In this case, is against, because it is slowing down. So overall, you can see the overall acceleration sort of need to be down to the sort of the lower left hand side. That's one method to do this. Another method might be a little more accurate, is to do vector additions, because we know acceleration is the change of velocities over time. So the direction of the acceleration is given by the change in velocity. Change means V2 minus V1. The velocity at your next instant minus the previous instant, right? So V2 is given, is in this direction, V1 is given. So you need to add these two vectors, well, subtract one vector from another. To do vector subtraction is the addition of the opposite of V1, right? It's V2. This is equivalent to doing V2 plus negative V1. Okay, and we know how to do that. V2 is in this way, negative V1 is in this way. We do a head to tail method. So delta V is in this red arrow direction, and that's the same direction as A, right? So both of this method will give you D. Now, I think the second one could be a little bit more accurate. Okay, very good. Now let's look at an example. It's really just an exercise, okay? So a lot of times remember like how when we were driving, right? If you're too fast around a circle, you find yourself kind of skidding away, right? So how come? It turned out that in order to maintain, to make that turn, you need certain kind of centripetal acceleration to change the direction of your velocity. Now, if your velocity is too fast, then you can only, you will need a bigger circle, right? The tighter the circle is, the bigger acceleration it requires. So given the acceleration that you can turn without skidding is 1.1 g. So that's 1.1 times 9.8 meters per second. That is what you have. At 100 miles per hour, how sharp of a corner could this car turn? Well, this is a direct application of the relationship between acceleration and velocity. So acceleration is v squared over r, the radius, right? So the radius r is going to be v squared over a. Let's plug in the given quantities. V squared is 100 miles per hour. Because the acceleration is given in units of meters and second, I'm going to change that to meters per second, and that's going to be 28 meters per second. Now you can Google how many miles is how many meters in the miles, and to do that conversion. So I have 28 meters per second squared over 1.1 times g, and that gives you 72.7 meters. That's how sharp of a corner you can turn. Now, if your acceleration is bigger, if this is bigger, you can see that if you can only provide your car how it gravitates toward the earth, the ground, it only provides such an acceleration, you need a bigger circle, right? So you can maintain this kind of turn if you have this much speed, but if you're faster, you need to go on a bigger radius, which means you find yourself skidding to the outside because your acceleration is just not gonna be that big. Okay, so this is really just a play on this direction. For centripetal acceleration, you can see in terms of calculation, there isn't too much. It's just the acceleration is v squared over r. Okay, so for next slide, I want to go to another document because I'm going to start dynamics discussion. So I'm actually going to show the checkpoint question you guys have already done. So, okay, we have a girl is rotating a rock. The rock is connected to a piece of string on a horizontal circle above her head. Okay, so at the point right here, if the string breaks right at this point, which of these arrows represent the path of the rock? Okay. So giving a top view looking down, if your string breaks at this point, then we in order to figure out the path, we need to figure out what is the velocity of the rock at this point. Okay, I got a message asking, does R stand for radius? Yes, R does stand for radius. So then in the previous question, the question is how big of a circle is asking for the radius of the circle. Okay, it is indeed for the radius of the circular path. Okay, for going back to this question, we know that at any instant, right, the rock have instantaneous velocity like this. Precisely because you have the tension in the string that provides an acceleration, so that your rock is rotating and following a circular motion. The direction of velocity is changing all the time. If you don't have this acceleration provided, well, the rock is just gonna keep with that velocity because that's the velocity it has at that moment. So without the acceleration, the rock is just going to have follow a trajectory looks like C, because that is the velocity at that instant, which is tangential to the trajectory. It is going to fall indeed. So not only it is flying away like this, it's also, and then later on gravity will be acting upon it. So it's like a trajectory down this way. But this is drawing a top view. It's not a side view, right? So it's not D. From a top, you can't really see that it's dropping. All you care that is going from left to right. So it's C, it represents the resulting path of the rock. Okay, now if you choose D, you might be right thinking that it's a parabolic motion. It is, but that it is from a side view. If you look at the top view, it's going to be C. The purpose of this checkpoint question is it is a perfect segue to our next topic. Is that an object without any other force acting on it is going to maintain the status of the motion. So when an object is moving with a constant velocity, or an object at rest will remain that velocity or remain at rest unless you have another force acting on it. So you can think about this question in terms of there is no force in the horizontal direction. Yes, you have gravity, but in the y direction. So the horizontal direction will forever maintain the same motion that it's always had, which is V naught, unless there is an external force acting on it. When you hit the ground, of course, that is another force acting on it to change the motion of the rock. So that is what we are going to discuss with Newton's first law. How do you describe it? An object at rest stays at rest, and an object in motion stays in motion with that same speed and in the same direction, unless they're acted upon by an unbalanced force. Okay, I need to update my share again because my screen didn't follow me. Let me do this again. Okay, Newton's first law. Okay, I'm gonna go through this again. An object at rest stays at rest, and an object in motion stays in motion with that same speed, same direction, unless acted upon an unbalanced force. So there is a lot of misconception or how people talk about motion. They will say something like, you need a force in order to move. You don't really need a force in order to move. If you're already moving and there's no friction, then you're going to maintain that speed and velocity forever. In real life, a lot of times we see an object need a force in order to move or stay in motion because there is friction. That's why the object always slow down. You need an external force to balance friction or overcome the friction. But if you can construct an ideal situation where there's no friction and the object remain in motion will remain in motion forever. So that is what Newton's first law is telling us. The comments seems to have a lot to do with free body diagram. How to do free body diagram. We'll do a little bit of that today, but mostly we'll have our practice drawing free body diagram when we do Newton's second law. Okay, so this is the second major topic in 1510. So first we did kinematics, right? Kinematics with all these kinematics quantities, velocities, position, displacement, acceleration. These are quantities which describe motion. Then dynamics are relating the forces and motion together, and mostly described with Newton's second law. We will have a lot of practice problem on Newton's second. Okay, so these are the second major topic in 1510. So before I talk about Newton's first law and all the other Newton's laws, first I want to describe the nature of a force, the concept of a force, as well as the typical common type of forces that we see in our lives and the common type of problems we're going to see. So I know that if you ask people what is a force, they can always tell you in some kind of language. They will say force is a push, force is a pull, or they might say force is the one that gives you an acceleration. But to be a little bit more exact, the force can be described as a type of interaction. There are 4 types of interactions in nature, 4 fundamental, and all the interactions we have in our daily lives or in the universe can be described as one of the 4 fundamental interactions. And you can say there are 4 types of forces. So forces is simply an interaction. If people ask you this question again, then you can just tell them force is a type of interactions. And there are 4 fundamental interactions. The one is gravitational interaction or gravitational force. Now you know what that is. That is responsible for the gravity we feel on Earth. Also, all the universal gravitational forces between any planets or between any 2 objects that has mass. We will talk about gravitational force later in later chapters of this course. The second type of interactions is electromagnetic interaction. That is so common. Pretty much all the type of forces that we talk about other than gravity can be explained using, has the nature of electromagnetic interactions. The third type of force is a strong interaction. These are the forces that holding the atoms together, holding the nuclei together. The fourth type is a weak interaction. That's radioactive. It's responsible for the radioactive decay. We are not going to talk about the third and the fourth. The forces we are going to do in 1510 are of the nature of the first two. But you know, in our universe, it's mainly one of those four types interactions. So now I want to go through the forces we are going to see in 1510. First is gravitational force. Gravitational force pulls the object down on Earth, directly downward, right? So the famous story that Newton's have an apple see the apple falling from the tree, and inspired him to relate this phenomenon and phenomenon of how Earth are orbiting around the sun. Two phenomena look so unrelated, but is described by the same physics principle, physics laws, that is universal gravitation. So gravity on Earth points always downward, and in terms of our symbols, we use F of G. G means gravity to represent it, or you can use W to represent it. In this case, it is weight, because our weight is exactly the gravitational force. If our weight is, let's say your weight is 135 pounds, then that means your gravitational force, the Earth acting on you with 125 pounds. Those are exactly the same thing. So you can say F of G or W to represent this force with the arrow pointing down. Gravity is also the only long-range force you will deal with this semester. Long-range meaning it's acting over a distance. Now your apple does not need to touch the ground in order to feel the force, right? Our sun does not need to touch the Earth in order to exert this force. It's acting up over a range. All the other forces that's coming up next has to be touch, a contact force. You cannot we do not have the long range force. So gravity, second force is called normal force. Normal force is a contact force. And now, for example, if you are, we're sitting on our chair right now, right? So there is a normal force acting on us, is supporting us. The chair is supporting us. So there is a force from the chair to our body that's pointing directly upward. Now, if your surface is inclined, like this frog, then there is a normal force pointing again perpendicular to your surface, supporting the object. Because in this case, your surface is, this is the surface, so your normal force is sort of also tilted, but is perpendicular to your surface. So this force is acting on the frog. So when we draw a free body diagram, you know there's a force acting on the frog pointing upward, perpendicular to the surface, and you use N as in the normal force, or F of N, the force of the normal force, to represent it, right? Then this is a contact force, right? If your body leaves the chair, you're not going to have the force. It's no longer supporting you, right? If the frog is not on the surface, of course, it's not going to have the normal force, okay? So you need the pushes. If you're simply touching the surface without pushing on it, you're not going to feel a normal force, okay? And the reason that we're pushing the surface because gravity is pulling us down, right? So normal force, if we're sitting on a chair, right? If this is us, we have gravity pulling down, we have normal force pointing up, supporting us, okay? So that's the second force I introduced here today. The third type of forces is friction, and there are two kinds of frictional force. One is a static friction, two is a kinetic friction. Okay, again, this is not updating. I have to do this again. Just 1 second, please. Okay, so I'm showing you a static and kinetic friction slide. So you can see that if your the surface is very slippery, you can see that the frog will probably try to slide down, right? The fact it's not sliding down, meaning there is a static friction preventing it from slipping. And the static friction is pointing along the surface. It's always along the surface, but upward. So in this case, F of S, little s, as in static friction, or if you want to just say friction in general, you can use little f or F of F to represent it. It means static, meaning that there is no relative motion between the object and the surface. The frog right now is static. That's why it's static friction. But if you're sliding along the surface, over the surface, you're in motion, you still experience friction, but it's kinetic friction. Let's say you're sliding along in this direction to the right, and there's a friction acting in the opposite direction of where you're moving. That's F of K, as in kinetic, okay? Or you can just say friction in general. If you only have one type of friction in your problem, you don't need to differentiate. You can label it as little f. Okay, so static and kinetic friction. Another type of force is called the force spring force. Okay, if you have a force, if you have a spring that's been compressed or stretched, then you will feel a force from the spring. If the spring is compressed, then you can see that you're compressing spring to the left, then the spring try to push you. In this case, the force is to the right, force of the spring. But if you stretch the spring to the right, then you can see the spring will try to pull you in. In this case, is to the left, force on the spring. Okay, so the spring force, you can see it can either push or pull, depending on if you're compressing it or stretching it. The longer you compress the spring or the longer you stretch the spring, the bigger the force is. Later on, you might see this relationship that the spring force is negative K times delta X. So it's always delta X is the displacement of the spring, meaning that if you displace it to the left, meaning that if you compress it to the left, then the force is opposite, is always to the opposite direction. The force is to the right, so there is a negative sign. Also, the force is proportional to the magnitude of delta X, that the bigger the delta X is, the longer you stretch it, the bigger the force is going to provide. Okay, this is Hooke's law. We will get to that later in the class. But here, all you need to know is a spring force can push or pull depending on which way you are stretching it or compressing it. The last type of force I want to introduce is called tension. Now, for example, if you have a rope and you're pulling on the rope, then you have a tension everywhere inside the rope, because it's continuous, right? In this case, if you are the one who holding this and drag it, but if we're analyzing motion of the sled, you can see your hand is not directly in contact with the sled, but it's the rope is in contact with the sled. So we will call this force the tension, as in tension inside the rope instead. So here we call it, there is a tension acting on the rope, on the sled, pointing in this direction, call it tension T or F of T. This tension is seen everywhere inside the rope, meaning that if you have a tension, if you have a rope, for example, let's say you have a pulley and you hang a rope down this way with one object, another object, right? Then this tension is upward, right? Pulling it up. This tension is upward, pulling object 2 up. Because they're the same rope, this is the same rope. So everywhere along the rope, you have the same tension. So this tension and this tension, they're the same thing. You don't have to label it tension 1 or tension 2 because they have the same rope. This is only true when you're dealing with a, we call it an ideal rope. Obviously, if you have something like a rubber band, or if you have a rope that have different texture at different places, and that's not the case. But we are dealing with just a homogeneous rope that is uniform and everywhere the same, that is not, cannot be extended. So so a lot of times in the problems, they will tell you you have an ideal rope, meaning that your tension in the rope everywhere is the same. So these are all the 1, 2, 3, 4, 5 type of forces that we are going to deal with in the course. Gravity always pulls down. Tension along the direction of the rope is the same everywhere along the rope. Normal force is always perpendicular to the surface. You need to have push, you have to be push on the surface in order to have the normal force. Spring force, it can be push or pull. Friction resists an object moving across the surface. Or if it's static friction, it prevents you from slipping. You can see tension, normal force, spring force, friction all require contact, right? If your rope doesn't touch an object, force doesn't exist. If your spring doesn't touch an object, there's no force. If you don't touch a surface, there's not going to be a friction. Only gravity can be long range, meaning that you don't have to touch the object. The earth does not have to touch an object in order to exert this force. Okay, so that's a lot of simply me talking through these forces. I'm just going to say just a little bit more so we can do our free body diagram together, okay? So what are the properties of forces? A force acts on an object by another object. For example, if I push you, so this force is acting on you by me, okay? There's always an agent. Who is applying this force? Is it spring, or is it the chair, or is it the rope, or is it the earth? There's always an agent that's providing it. It's acting upon an object. There's an object that force is receiving this force, in other words. Now, force is a vector, just like acceleration and velocity. It's a vector. It has both magnitude and direction, okay? You have to tell people not only how large the force is, you have to tell people in what direction the force is. Contact force requires contact between the agent and the object, right? If you don't touch someone, you cannot exert a force on them. If the rope doesn't touch an object, you cannot exert force. Long range forces acting over distance. In this case, in our course, we only care about, that's the gravity. Later on in second semester of intro physics, you will do electric force, magnetic forces. Those are long range forces as well. But in 1510 is only gravity. Okay, so now let's talk about free body diagram. So what is a free body diagram? It's a way that that we draw. It's a diagram we draw to help us visualize all the forces on an object that we're interested in. So there is an object. Let's say we're interested in the object of this block. Okay. Then we are going to draw all the forces on the block. We're not going to draw forces elsewhere. We're not going to draw the force on the person. We're not going to draw a force on the earth, not on the surface of the floor, but only on the object. So you're sort of freeing this body away from other surroundings. You're going to focus on this object. And you model all the forces using arrows. You put them, all these arrows on the object and simply label them. Okay, so for example, you have a person pulling on literally a ton of weight. So it's a very heavy block. right? So that implies that most likely this counterweight is not going to be moving. So I'm going to tell you that it's at rest. Okay, so let's think about all the forces as acting on it. So isolate the object and think about all the other objects that is in contact with this object or can act upon with a distance that is a gravity, right? So in this case, we have gravity acting on the object, right? So going downward, this is gravity on the object. So here the object become just a square block. You don't have to draw the object so perfectly, just model it as a block. Now, the object is also in contact with the floor, right? So the floor is going to provide a normal force supporting the object. That's the normal force upward, right? Perpendicular to the surface. The surface is level, so this is going to be perpendicular upward. Normal force. Now, the block is also in contact with the rope, right? Pulling to the left. So you have a force by rope, or you can call it tension. So in this case, I'm going to label this gravity as in F of G, normal force as in normal, rope as in tension, and little friction. Now, how do I know there is a friction? Would it be okay if I draw this weight as in F of G, normal, and tension, and be done with it? Would that be correct?
Didn't specify if the surface had friction.
I'm sorry, Eric, can you say again?
I don't think the question specified if the surface has friction.
Yes, we do need to specify there is friction because it is at rest. If there is no friction, do you think the object could be at rest? It will not be, because you will only have tension is going to start moving in your direction of the tension. It's at rest. This is really the analysis using Newton's second law. These forces need to be balanced in order for the object to have a zero acceleration. It's at rest, right? It's not having any acceleration. So you definitely need a friction in order to balance out the tension. In this case, it's also not moving, it's actually a static friction. So the problem implies that I have 4 forces here, 2 in each direction, and they are all balanced out in this case. So that's called a free body diagram. Okay, let's start with a quick question. This should be straightforward. Have a block simply sit at rest on a horizontal frictionless surface. Which of these sketch is a correct free body diagram? And I'm going to let you vote. I don't think we need to discuss on this one. Okay. Okay, I'm seeing the comment. Someone lost their sound earlier. If you couldn't hear me, if it's because I'm too far away from my mic, just let me know. Sometimes I moved a little bit further. I just will try to get close as possible. Someone said that they restart their computer. That seems to have figured out the answer. Be able to hear the sound. Okay. All right. Any last minute vote? I'm sorry, I kind of wrote the answer at the bottom already. I'm sorry. But pretend you didn't see it. Think about this for yourself. The poll is still going on. I have 77 out of 81 votes in. So 5 more seconds if you still want to vote, okay?
I don't think I got a poll or something. I don't think I got a poll.
Sometimes you have to click it if it's closed. You have to click it for it to show up.
I don't see anything on the bottom.
Okay. We'll try for the next question. See if your poll shows. This one, I'm going to go ahead and close it. All right. So let's see our results. I'm glad we all agree, at least in the vertical directions, right? You have two forces. D votes for, it's also balanced on the horizontal direction. So let's go back to the question, take a look. For the two vertical forces, can you guys label it? What is a downward force? What's it called? Acting on the, yes, thank you, Cindy. It's gravity, right? And what is the upward force?
Normal force.
Normal force. Very good. Now, gravity acting on a block by Earth, normal force acting on the block by the surface, okay? And these two, now you have to think about the block is in contact with other objects. It doesn't tell you that there's something pulling the block or pushing the block, right? It's not in contact with anything else. So you kind of not going to be able to have these two forces. Where would it come from? So not any forces in the horizontal direction. So really just A. Very good. Okay. Now I have another question. I don't have the answers for this one, so you have to figure it out. A block slides down a frictionless inclined plane, a ramp. So basically it's smooth, frictionless, it's a ramp. Which one of this represent the forces on the block? Okay. I will put the pool up, and if you couldn't see the pool, I hopefully this time will show up for you. Okay. Let's see. So now the pool has started. See if it shows up. Okay, let's go for another 15 seconds to finish voting. Okay, all right. So I'm gonna go ahead and close the poll and then continue. You can see the results. We actually have majority voted for A. And the second popular answer is D. Okay. All right. So again, we are curious about the motion of the block, right? Free body diagram has to be on the block. All the forces has to be acting on the block. So let's go through the forces that we can think of. So can anybody just simply give us one force, one at a time?
Gravity.
Is the normal force perpendicular to the surface of the object?
Okay, the normal force acting on the block. Because the block is in contact with the surface and the surface is providing a supporting force that's a normal force perpendicular to the surface. So this direction. Okay, very good. Any other forces?
Gravity.
Gravitational, yes, very good. The gravity of from the earth to the block, pointing always perpendicular downward, always downward. Okay. Okay. Is there anything else? Those of you who voted for A, what would this be?
Friction.
Friction. If there were friction, yes, it would be going against the motion, but it is actually a frictionless surface, which means we don't have to think about friction. Normally, yes, we do. In this case, since it's given, then no friction. Okay. So what is this force then? If you cannot name it, it probably doesn't exist, right? In order to have such a force, you need an agent. You need some object to exert the force on the block. There is nobody is dragging the block down, pushing the block down. So this force probably doesn't exist. I understand that you want to draw that because the block is sliding down. You feel like there is a force that making it go down. So what is responsible for the block sliding down? What do you think?
The summation of gravitational and normal force results in a velocity in that direction.
Ah, very good. You can view these forces as we talked about is vectors. So if they're vectors, meaning that they bear the vector addition rule. The force and normal force coming together, an overall effect give you the overall effect. I don't want to draw this as a force, not to confuse you, but overall effect is going down, the plane. Now, another way to look at this is to think about this force, this one as in a component of gravity. So a lot of times we view gravity as two components. One is sort of responsible for pushing it in this way. Okay. Another component is responsible for making it go down the ramp. Okay, the one that's pushing it in is being balanced out by normal force, and the one that's making it go down is the one that making it go down. Okay, so we can view this as a component of gravity, but it's not a separate another extra force. That's why you cannot draw it in your free body diagram, especially if you already have gravity, then you should not draw the component of gravity again. The component is really just our artificial way of breaking it down. It's not an extra force. So D is the correct answer here. Okay, just gravity and normal force and nothing else. So as we said, the superposition of the forces simply by adding them together, the effect of all the forces, so you have, let's say you have 5 forces, they can all add up to be one vector. Then the effect of those 5 forces is equivalent of having this one net force, one vector, overall vector. They obey the superposition principle, okay? Okay, I have another question here. Because now we have if we're talking about the effect, we have to talk about the sort of the superposition. We have two forces. If those two forces simply are acting in equal and opposite directions, then they cancel, right? 5 upward and 5 newtons downward, they cancel. But if one of them is stronger, then overall you have a net force that's in that direction. So I'll give you guys a couple minutes, a minute or two on this question. If you have a mass here that's in the elevator is hung by this string, and the whole elevator along with the mass, so everything in it is accelerating upward, which means the mass itself is having an upward acceleration. So which one describe the relationship of tension compared with okay, I'm just gonna tell you this is force of gravity of the mass. Okay, so how do they compare? I'll give you guys a minute or two to think about this in groups. Okay, as people come back, please put in your vote for this question. Okay, another 10 seconds. Okay, all right. Let's close to the vote and then we can take the vote. Okay. So we have majority of answered A or B. B is majority. So tension and the force of gravity. Now, if I ask you guys, if you have an object with let's say 10 pounds of force upward and 10 pounds of the force downward, the overall, these two forces will add up to be how many pounds? So these two vectors, one up, one down, with equal magnitude, but opposite direction. That would be 0, right? So if that's 0, then you will not be speeding up or slowing down, right? You will not be having any acceleration. In this case, if it is accelerating going upward, meaning that the force upward has to be bigger than the force downward. Here, we are really just looking for a qualitative sort of analysis here. In Newton's second law, we will do this a bit more clear. You will see the relationship between the force equals ma that we will discuss in next class. Here, we're just looking for a qualitative answer here. If one of them is larger, if this one is much larger, says 20, then you can see overall it has an effect of the force pulling upward, right? Giving it an acceleration going up. So if it's accelerating upward, meaning that the tension must be bigger than your gravity. Okay, the tension is the one that's pulling the object up. So tension and little mg, or f of g, one must be bigger than the other. Okay. So that's Newton's first law. The body acted on by no net force will maintain the same velocity. And again, this is implied. So a body will remain at rest or remain in motion with the same speed and same direction, which means if it's same speed, same direction, there's no change in velocity, which means no acceleration, right? So unless there is an unbalanced force. So if you have a balanced force, which means you have a net force of 0, then the body is not going to have change in speed or direction. It will have no acceleration. So this is implied in Newton's first law. So if net force is 0, acceleration is 0. Okay? Which means velocity would be constant. Or if it was arranging at rest with 0 velocity, it's going to maintain that 0 velocity. If we're moving with some constant velocity, then it's going to continue moving with that constant velocity. So these two interpretations are sort of implied by Newton's first law. So let's see if we can answer the question. Here, let's say you have a Superman is pulling a ton of weight. Because the Superman is pulling on it, now the weight is being pulled by with a constant speed v to the left. Okay, so v is constant. So, and it's asking you about the net force. I'll let you guys vote on this, okay? All right, 15 more seconds. Okay, any last minute vote? So I'm going to go ahead and close. This is our results. Our majority voted for C to the left. Second popular answer is E, it is 0. And there's some other answers there, here and there as well. So how do we begin to answer this question? What are your thoughts? The direction of the net force that's acting on the weight. So we know that there are many forces, right? There's gravity, there's mobile force, there is tension, there's probably going to be friction, but it's asking about the overall, all the forces adding together, the net force. What do you think about the net force? So if I say because it's moving to the right, the net force is also going to be to the right and choose C, do you think that's correct? Yes or no? Anybody? There's a very key and important information in this question. Is it's being pulled to move at a constant speed, okay? To the left. So that implies the acceleration is what?
0.
Is 0, yes. Okay, we just talked about a body moving at a constant velocity has no net force acting on it. You wonder, okay, maybe at the beginning, the person has to apply a bigger force to get it to moving in the first place. But now we're just looking at the snapshot, and once it's already moving, it is moving at a constant speed with the same direction all the way through. So constant velocity acceleration is 0, meaning net force is also 0. This is inside Newton's first law. Okay, so the net force has to be 0. So E is correct. C would have been correct if you're asking about, okay, it's asking about a time, sort of a time before the snapshot. If the ton of weight is standing here at rest at first, and then someone got it to move, right? Yes, at some point it needed an acceleration, but now it's asking when it's already moving, it's moving at a constant velocity. Okay, so the correct answer is E, it is 0. There is another question, I'm going to talk through it. But just a way how you explain this. You put your book on the bus seat next to you. When the bus all of a sudden stops, right? The book slides forward off the seat. Or a lot of times when our car, you hit the brakes too hard, you find yourself moving forward. Why? Now, in the past, people say it's inertia, but really it's just an explanation of Newton's first law. Because the book or yourself will remain that velocity unless there is a force acting on it. So in this case, the brakes make the bus change the motion. The bus decelerated, but the book didn't, right? The force hasn't acted on the book yet, or your seatbelt has not acted force on yourself yet. So you're simply going to remain that same speed unless the force takes an effect. So why would the book slide off? It's simply just maintaining its original velocity, because the brake is not hitting on the book, it's just on the bus. So you're simply saying why is it's remained moving. The bus has changed the motion because there is an external force decelerating the bus. But because of Newton's first law, the object was at motion, will remain in motion. So it simply remained moving. That's how you answer the question. The same way when you are leaning forward, when you hit the brakes, is yourself, you're simply maintaining that motion, right? Until your seatbelt provided a force for you to kind of slow down together with the car. Okay, so it's a subtlety of the language, how you explain physics correctly. So the correct answer is simply keep moving unless there is also a force acting on it. Okay, so that's all for today. we have finished our discussion for Newton's first law. And on Thursday, we will start our discussion on Newton's second law. Okay. All right. I'll see you on Thursday.
Thank you, Professor.
Have a good one.
Thank you. Bye,
Thank you.
everybody.
Thank you.
Thank you, Professor.
Thank you,
Bye.
Professor.
Thank you.
Professor?
Yeah.
I'm still having trouble logging into my account.
Okay.
It keeps saying the same thing. I tried using my dad's computer too, and it says the same thing. I use like a couple different devices, even my phone, and when I try to reset my password, it doesn't even let me to reset my password.
Okay. I'm also getting a buggy message myself. How about you try again this afternoon?
Okay.
And I remember someone in the past did call their customer service, get it figured out.
Mhm.
You know what? I'm emailing the programmer. He only in charge of the sort of the content area, but
Yeah.
I'm gonna shoot him an email just saying, by the way, this is happening. We're having this technical difficulty right now. Maybe if you know someone, they can take a look at their website for the sort of the entry database. But I will do that, and you also try again later this afternoon, and just email me and keep me posted.
Okay, for sure. And is there like a specific browser I need to use for that website? Like
I
maybe.
don't think
Chrome?
so. I think any browser would work. I use Google Chrome, but I think any browser would work.
All right. Okay, for sure. I'll keep you updated then.
I'm sorry about this. Thank you.
Fine. All right. Thank you very much. Have a nice day.
You too. Bye.